I want to go over some concepts behind the mechanical systems in a house. I think it gives a broader understanding of how and why things work the way they do. Hey, come on, buying a house is a major purchase. I want to help you get the most out of your house so that you can enjoy living there and keep repair bills to a minimum. First, air circulation. Let's look at the house for a moment from the standpoint of airflow and heating, for example. Floor and wall furnaces are a point source of heat, and heat from one spot has to go throughout the house to warm it. Depending on the layout, it's doubtful the house will be heated evenly. On cold nights, you might want to use a small space heater to warm the bedroom at the end of a narrow hallway, for example. Now, on the other hand, a forced air furnace uses a blower to force the heated air throughout the house. Ducts carry the air to circulate through various rooms. But if a door is closed, the normal airflow can't include that room in the circulation. The room will get either too warm or too cool. Is there a centrally located return air grill? Putting stuff in front of the grill blocks the flow. The air can't circulate. The return air grills have to remain open and accessible. Exhaust fans also need good airflow to work properly. Bathroom exhaust fans do not remove odors and moisture from the room. Bathroom exhaust fans remove the air that holds the odors and moisture. And the fan can exhaust that air only as long as fresh air can come in to replace it. Otherwise, the fan blade will turn, but it's just freewheeling, spinning in place, not moving any air. Where does the air come in? Where does the air go out? The fan circulates air along that path. So if the window is open, as you can see, that will take care of the moisture coming from the shower, but it will do little to exhaust the odors from the toilet area below. On the other hand, if there's a gap below the door, leave the window closed, the fresh air will flow in from under the door, up past the toilet area and out. Kitchen exhaust fans and clothes dryers are often subject to a different set of concerns. Sometimes the kitchen exhaust fan just blows air through some sort of filter that absorbs odor, and the air is circulated back into the kitchen. Other times, the kitchen exhaust fan is ducted as a clothes dryer should be. Where does the vent exit the house? Try to estimate how long the run is and how many twists and turns it takes along the way. Every transition, every bend, every elbow, every foot of duct retards the airflow. If the duct run is long and convoluted, little or no air may actually come out of the other end. You want the duct run to be as short and direct as possible. Let's talk about size. Generally, does size matter? Basically, the rule of thumb is the bigger delivers in greater quantity. You have a greater resource to work with and can have more things running at once. With water heaters, the larger tank means you have more hot water. So you can run a load of dishes in the dishwasher, clothes in the washing machine, and then you can take a shower without running out of hot water. With the electricity, the bigger breakers and larger wires mean more amperage, so you can run maybe the microwave, the blender, and the toaster at the same time without blowing the circuit. With HVAC, heating, ventilation, air conditioning, it means the bigger air duct delivers a greater airflow to different parts of the house. Bigger does deliver in greater quantity, but sometimes it's more a question of materials. What's better, a 3/4 inch diameter galvanized pipe or a 1/2 inch diameter copper pipe? Rust and corrosion will close down the inside diameter of the galvanized pipe. Galvanized pipe will rust out and leak. Galvanized pipe uses threaded fittings that can be harder to repair. What's better, a 20 amp aluminum wire or a 15 amp copper wire? There have been serious problems with aluminum wiring. Houses were wired with it at one time, not anymore. Repairs are trickier. Aluminum wiring requires special outlets and switches. Bigger delivers in greater quantity, but bigger is not always better. If the furnace or air conditioner is too small, of course it will never adequately heat or cool the house. But if the furnace or air conditioner is too large, the thermostat can shut the system down too quickly before some parts of the house are heated or cooled. The system has to be sized for the house. Pool systems also need to be sized properly. A 2-inch diameter pipe delivers about 70 or so GPM, or gallons of water per minute. An 1.5 inch diameter pipe delivers much less, about 40 or so gallons per minute. Pumps and filters come in different sizes as well. A big pump with small plumbing strains the pump. It's trying to pull more water than the pipes can supply. Big pipes, big pump, but small filter stresses the filter, and the inner components will wear out prematurely. Again, for a system to work efficiently and cohesively, the components have to be sized for each other. Let's talk about efficiency. Basically, how much bang do you get for your buck? When you're talking about HVAC, heating, ventilation, air conditioning, there are some standards to know about. For gas furnaces, efficiencies are expressed in percentages. Look for the AFUE percentage. AFUE, that's annual fuel utilization efficiency. The furnace is 80% efficient. That means 80% of the fuel went to heat the house, 20% of it was wasted. The higher the percentage, the more efficient the furnace and the better the value. For heat pumps, look for the HSPF, Heating Seasonal Performance Factor. This is a measurement of how efficient the heat pump is in the heat mode. The higher the number, the greater the efficiency. For cooling, look for the SEER rating, S-E-E-R, Seasonal Energy Efficiency Ratio. For every watt of electricity you put into the system, how many BTUs of cooling do you get out? The higher the SEER rating, the SEER rating, the more efficient the system. Let's talk about insulation. Insulation prevents heat loss or heat gain. The R value tells you how well the insulation does that. The higher the number, the more effective it is. Insulation comes in different forms, but here's some idea of what you may find as you look at houses. Sometimes insulation is blown into the attic or walls of a house in little tufts of cellulose. The R value of blown cellulose insulation is 3.7 per inch of cellulose. You've probably seen fiberglass insulation. It has an R value of 3.14 per inch of thickness. And there is expanded polystyrene with an R value of 4.0 per inch of thickness. Use anything up to R15 in 2x4 walls, anything up to R21 in 2x6 walls, or maybe under a house that sits on a raised foundation. Use R30 or better in attics. The Department of Energy has calculators to help you figure the relative costs of heating and cooling a house with different R values of insulation. You put in your zip code and it figures it out for your area. Annual energy costs with household appliances such as refrigerators, freezers, room air conditioners, washing machines, and dryers. Look for the annual energy cost to run it. See how many gallons of water the washing machine uses per load. Either call the manufacturer of the appliance or look at their website. Let's talk about roofs. What is a roof supposed to do? Well, that may sound like a simple question, but if you think about it for a few moments, so much of roofing will make so much more sense. A roof does not simply keep water out of the house. It should, but if that's the way you approach a roof, you can create situations that over time are going to fail. Instead, a roof should shed the water. Put a drop of water on top of a house. The roof should either direct it to the side or down a slope to the edge where it is further channeled or simply drops to the ground. Okay, so first, the higher the pitch of the roof, meaning the steeper the roof, the more easily it sheds water. The lower the pitch, meaning the flatter the roof, the more potential there is for puddling and problems. So if you are considering a house that has a flat roof, check carefully for wear and possible water damage. Also make sure the paths are clear for the water to run off the roof. Look to see if there's anything that might keep the roof from shedding water. What obstacles are in the way? Are there dormers, ventilation pipes, weather vanes, whirlybirds, or skylights? Does the water have to go around something? It becomes a maintenance thing. You have to keep the pathway clear. Does the water have to go over something? It will eventually when the water puddles up enough to go over the obstruction. But when it stops raining, the puddle is still there until it evaporates. Think about it. Puddles are leaks waiting to happen. Pool circulation systems. Efficiency is designed into the systems. The pump has to work to move water. TDH, total dynamic head, tells how much work the pump has to do. Everything in the circulation system works against the pump. Every foot of pipe, especially pipes with smaller diameters, every turn and bend it takes along the way to the equipment. The filter adds to the load. Valves, especially backwash valves, add to the load. So does the heater, as well as every foot of pipe and every turn and bend going back to the pool. Is the equipment on the same elevation as the pool, or is one uphill from the other? That's more work the pump has to do. By the way, if the equipment is higher than the pool, it's that much harder to prime the pump because to start with, the pump has to pull the water uphill. Anyway, these factors work against the pump. Add them all up, and you get the total dynamic head pressure. It's the amount of work the pump has to do just to overcome the system itself. As you can see, the shorter and more direct the run, the more efficient the system is going to be. More energy is spent moving water, not simply fighting the design of the system. You need to run the pool's entire volume of water through the filter at least once a day. That's called the turnover rate. If the motor pump has a flow rate of, say, 29 gallons per minute times 60 minutes in an hour, the pump has a flow rate of 1,740 gallons per hour. Let's say the pool holds 10,500 gallons of water. 10,500 gallons divided by 1,740 gallons per hour is about 6 hours. So for the pool in our example, you'll need to run the motor at least 6 hours a day. Call the electric company and find out up front what it will cost each month to do that.
I've got a lot more great stuff for you at houseiq.information. If you like what you've seen so far, do me a favor and tap the subscribe button so you don't miss future videos. And click the link to watch some more great stuff right now.